So the idea today is we're going to try roughly at 1 o'clock to go up to the lab for those of you who haven't done the threading activity and get at least started. The tools will be up there over the weekend and it's due next Tuesday. That's when you have to turn in, so the tools will be up there and available for you anytime the lab's unlocked, which is most of the time because there's almost always somebody in there. So does everybody, have you either had your meeting with us or you have one on the books for tomorrow? Yes?
I think so,
Okay.
because
Okay.
yeah.
So that has to be done by the end of the day tomorrow. And we'll go over kind of what the next step is with the project at the end. And we do have an activity at the end of the class today that if you've already done your threading activity, you'll probably be able to do it and you'll be done by the end of the class time. And if you haven't, then you might have to do one or the other. It won't take too long. All right, so today we're going to talk about prototyping of electronics and different ways to do that electronics prototyping, including soldering and basic skills like that that you might need to complete your projects. And so when you're building your electronic device, the main thing to consider is what level of permanence do you need. So if you're just trying something out and you don't know if the design is going to work, or if you don't know if it's going to work for your application, you want something that's pretty temporary. And these can look a little scary. They don't have to be pretty or robust necessarily. They just have to tell you if your idea is going to work. So here there's a box with aluminum foil and a breadboard like you've got, and a crazy mess of jumper wires on a breadboard there. But this actually saved a lot of time. This is a prototype that I built a year and a half ago or so. And I didn't spin a custom circuit board. I didn't spend all this time making something permanent, which was good because it turns out that wasn't going to work at all. So I lost 2 hours building that, tested it, said, oh, this isn't going to work. Took all the parts off the breadboard, put them back in my box, and was ready to go again. But as you can see, it's not very permanent. If you were going to run the biax on something like this and you intended on using it for the next 5 years, that might not be where you want to go because it's pretty easy to pull parts out, pull wires out, hard to trace down, that kind of thing. There's also permanent, or I would say even semi-permanent, building it on what's called Variboard or perf board that we'll talk about in a little bit. This is something that probably looks familiar to a lot of you that have worked in the lab. These parts are soldered down, and it is a permanent construction, but it's possible to change without too much trouble. We're not having to go have new parts made, new circuit boards made to change something in this design. And it can still look a little bit rough and ready because maybe you're only going to build one of these things. It doesn't make sense to go to a full production quality build if you're not going to build one in your lifetime of the equipment. And then there's a finished or production environment where you either need to build a lot of these things. I don't think anybody's going to be designing something that's rolling off a factory line, hundreds of thousands of units probably. Research equipment is generally a lot more custom than that. But maybe it's something that's going to be used for a long time, and you want to make a nice control panel for it, something that's going to be robust, something that's going to hold up to abuse, as a lot of lab equipment ends up taking over the years. So if you look at controls, like turn the biax on and off in the lab, and turn the chiller on and off up in our lab, those have lasted a long time, and they're built very much in that finished or production style. So breadboards, like I said, are the best way to do quick, cheap, dirty prototypes. All the parts just stick in, you can test your design, and pull the parts right back out. And today you're actually going to get a little bit of experience with them. We're going to build a simple circuit on the breadboard that you've got. And you can see, I mean, this, for example, here they're trying to write some data to an SD card, and they didn't have an adapter to plug an SD card into a breadboard, so those are made. So they just soldered a bunch of wires onto the connectors on the SD card and plugged them in. Is that reliable? Not really, but it's going to tell you if this design has a chance of working. And also, this is a medium-sized breadboard. For really large prototypes, I use breadboards that are like a Google pad size. So you can get them in all kinds of sizes. And some of these, you can see their tabs, this is actually 2 smaller boards that snap to.
Something to add to what John just said, it'll tell you, this breadboard will tell you if it's going to work for sure. but it'll also help you think. It doesn't, you know, you start to build some part of this thing, and it is tangible enough that it's a little bit more than even sketching it out. So it can be a really nice way to sort of think through what you're trying to do in a active learning style if you want.
Yeah, definitely. And if you have your breadboard, you can actually go ahead and pull it out and take a look at it as we're talking about this slide.
There's the thing that you have been playing with, put together, whatever, probably you already tied it down under the board.
Right, and so remember we pulled there's a key stick on the back to stick it down. If you were to pull that adhesive off the back, you would find that there are a bunch of these things that stick up through all the holes here. So those are little spring clips, and there's a picture here, so you don't have to do it. Because if you pull one out of your breadboard, good luck getting it back. That doesn't happen. You generally don't want to do this. But the idea is that these columns, so there's generally 5 holes, that's the case on yours, are all connected. So these little metal strips run column-wise and look like this. They're separated in the center by this channel. So this column is not connected to the column below it. And then across the top and bottom are power buses that make it easy because you have lots of things that tie into ground and lots of things that tie into your power supply. So they run the entire length of the board on these top 2 and bottom 2 rows. And this board is immediately marked plus and minus for you. And since you have 2 of these and they're not connected, you could have, say, this plus be a 5-volt supply and this plus be a 3.3-volt supply, or a 12 and a 5, or however you want to do it. But if you do want to use, say, the ground on both sides, you have to make sure that you tie them together so it doesn't jump the wire across. Is everybody comfortable roughly with how breadboard's laid out? No questions about how to use it? Okay, so 22 gauge wire is what you want to use if you're sticking things into this. That's what it's designed for. The other thing is when you buy components, resistors, capacitors, like I think a lot of times they come, if they're through-hole components, which is what all these are, everything that we're going to use, they come on this tape that's got some glue, and this makes it easy to feed into big production machines. What most people do is they grab the tape and they rip it off the end of the component, and they pull the component out of the other side and they stick it in their breadboard. And there's lots of wonderful adhesive that's left on the ends of the component leads by that tape. And that adhesive, one, gets down in those spring clips and will eventually gunk them up. And more often than not, if your circuit is acting really weird, it's going to be because it has an intermittent connection to that spring clip because of that adhesive that you left on there. So you can either scrape it off with a pocket knife, a razor blade. The easiest thing to do is these leaves are really long and you never need them that long. So the easiest thing is to take a set of cutters and go in and cut them out. Leave the piece of the tape. When you pull your resistors out today to use, Sparkline has already done that for you. They actually just have this giant machine that they feed this into and somebody stands there and cranks a handle and it just cuts all the resistors out.
John, you want to go back on the slide just a second to make sure it's kind of clear. You know, there's the term bus, and if it's a power bus, and you hear that term all the time in electronics, like computers have these buses that relate. The idea is that it's short for omnibus. It's everywhere. And it is this strip that's here, that, you know, that runs around the outside of this thing in particular places. And actually, I think I'm pointing to the right thing here, but the idea is, you know, a strip of metal that has that is omnibus, that has that power, whatever you put on it, everywhere. It's available everywhere. And it is a super common thing in electronics. You want to make sure there's not a jargon term for the bus.
And for server racks or sometimes laboratory equipment even, you want to make sure that everything has the same ground and a good solid ground. You can buy these large copper bars, ground pluses, that you tie everything into. And so with the breadboard, there's a lot of ways to create your circuit. These 2 circuits do the same thing. For example, you can see the parts are laid out slightly differently. In this case, when you press the button, the LED comes on. Not a very exciting circuit. You can see here we've got power coming down to the LED, and we have a resistor that goes into one side of the switch. clear, power, goes to the LED. Here's the resistor, and now it goes horizontal to another column. Instead of going across the center here, into the switch down here. They both do the same thing. And it just takes some practice and some experience when you're laying out your design on a breadboard. The first thing you do, you'll be having parts, one part goes over another, and you're trying to thread a wire through somewhere, and it's a little bit of a disaster. But then as you just do it more and more, you can kind of see what's going to work well in terms of layout and what's not. But breadboards do not come without their problems. This is especially true if you're trying to do anything high frequency. So fast digital communications, high-speed serial, high-speed, any kind of talking to sensors, or RF, if you're trying to do something with transmitting and receiving, radars, XP, anything like that. There can be problems because, and there's a video of this on the website, but when you put two connections into a breadboard, it's two conductors separated by a little piece of plastic, right? So what we've got is something that's connected to a signal, and something else that's going off somewhere. And does that look like anything familiar yet? We haven't talked about it. It's a capacitor. So you have two conductors separated by a dielectric. There's a tiny bit of capacitance on it, and it's on the order of picofarads. And the video online shows you measuring that. But that can play with your signal a lot. So this is a square wave, so 0, 1 volt, 0 volt. You can see there's a little bit of ringing on there. That's actually due to the what's called parasitic inductance on the board, but don't worry about that, we'll get there. But as you increase the capacitance, that square signal becomes increasingly rounded until it looks like this sharp tooth shape. And it's a function of frequency. So if this were a really high frequency, if you were trying to do something in the gigahertz range on your breadboard, what you think is a square signal is now a sharp tooth and never even gets up here to 1 volt. So it causes all kinds of problems. So breadboards are not good for high frequency design, but everything that you do in the class, they should be fine for. And if you zoom in there, you can actually see how this ringing from the parasitic inductance on the breadboard makes your signal look really pretty as well. A semi-permanent construction technique that you're going to see a lot is perf board, vero board. It goes by all kinds of trade names. The idea is, and this is a picture of a board that's in the biax right now. It's actually laid out very similar to your breadboards. So all of these holes are tied together by copper traces on the back of the board. You can see that we just plug parts in, run wires point to point where you need to, and that is a pretty permanent construction line. Chris, how long have those boards been in here?
93, 94, and 92. They were all built then.
Yeah, so they've lasted quite a while. Eventually, things do start getting brittle in age, but overall, for a one-off circuit, that's a really good way to do it. And there are more complicated ones. For example, this is a shield that you can get to plug onto your Arduino. And here there's an SD card slot, there's a GPS, there's a battery to keep track of the time when it's unplugged. And then there's this little area where you can prototype, where you can put lights, sensors, switches, level shifters, all kinds of stuff on there. So there are a lot of tools out there to help you with perf board and vero board construction. It can be done really poorly, and that causes all kinds of problems. This is seen more often than not with people that are beginners. It's not something you want to do because you see you have all these copper pads on the back that help you solder joints, and they say, well, this is great. I'm not going to run any wires. I'm going to make a bunch of solder bridges between these and make my own sort of printed circuit board. And that is a nightmare to ever do anything to. If you have a soldering iron, you're trying to change something, you're going to unsolder a connection that you didn't mean to, or you just do not want to do it. It's not reliable at all. This is the technique that's used most frequently for high-speed or RF design, and it's called Manhattan or the dead bug technique. The Manhattan comes from, if you look at this from the side, these kind of look like a skyline, called Manhattan. And dead bug, you'll see on the next slide why it's sometimes called dead bug. This is just a piece of sterling material called FR4 fiberglass, and it has copper that's deposited on both sides through a chemical process. It's what they make printed circuit boards out of, but here we don't do anything. We just take a plain copper board, and you can see solder components directly to it. So for example, the entire top plate is going to be ground, most commonly. And then for other connections, you can glue on these little pads that are other pieces of that copper coated board and make little islands to do your connections on. And so here's a bunch of them. There's some custom ones here for integrated circuit, so you can glue it on. This is a really, you can see when it's done well, it looks just about like art. But it takes a long time to do this type of construction, and it is pretty permanent. You can add or remove islands somewhat, but you can imagine it's hard to change a lot. And there are all these connections that are not too many here, but some of these that are flying through the air. So occasionally you hear this called fly wiring. All right, here's dead bug. With dead bug, you take the integrated circuit and some super glue, you turn it upside down, and glue it down to the board. And then you just wire all of your components directly to the legs. Once again, it looks really messy, but if you're prototyping a high-speed design, this is the best way to get no strained up intercapacitance, or low strained up intercapacitance that you can.
Although the driving nuts trying to set the connections up, because normally when you look at an integrated circuit, you used to look at all the numbers, you know, from the top, and then you look at it upside down, it's got backwards. Yeah, you get about
Yeah.
where's the pin one, and.
And as you can imagine, it is it's time consuming to do the layout for this, and it can be kind of frustrating. And it's also not very mechanically resistant. You can make it very well, but I would not put this in a box that's going to get tossed around by UPS and thrown on a plane and taken to the field, right? And you see variations of dead bug all the time. For example, this is stacking a bunch of memory chips. This is actually, you hear about stacked memory. This is stacked memory with a bunch of resistors going there. So people can do some pretty crazy things when it comes down to it for prototyping. And since these copper clad boards can be soldered, it is not uncommon with radio frequency devices. You will often want to have them enclosed in a grounded housing to keep radio frequency from the outside from getting in, keep radio frequency from the inside from getting out, so you don't interfere with things. We can hear the radio on the biax sometimes because of radio frequency interference, RFI. So some people build the entire enclosure for their project out of these copper boards. They just cut them, drill them, solder them together, and they get these really gorgeous looking enclosures. So that's a pretty cheap way to make enclosures. Wire wrapping is a technique that is still used mostly for digital design, though not very commonly anymore. We'll talk about what's been replacing it a lot, but especially with large computer designs and the other computers that use wire wrapping. You buy this special wire, this wire wrap wire. It's a very certain gauge and has a certain thickness of insulation. And your components go into holders that have these pegs that are actually square. You go down from the top. You stick the wire into a tool. There are hands and there are actually battery powered, kind of like air guns, to do this. And you stick the post into the tool, you pull the trigger or turn the tool, it strips the wire and wraps the wire around that post. And the wire gets little indentations on it, on the square corners, and it's a very, very secure connection. It's okay for high-speed design, because you can imagine there is a lot of interference. You have a lot of signals on different wires that are passing directly over each other. But it was used quite a bit, still a viable tool. Also, you can change, so you can have multiple wire wraps. Let's say you could have 4 or 5 connections wrapped on top of each other here. So this pin can be connected to several things. And you can change it relatively easily. Put the wire wrap tool on, turn it to the left, the wire comes off, and you can move it somewhere else.
So if you ever pull the board out that does the digital counting on the biax, the so-called, computer that's on there that we use to ramp up or ramp down something, it's all done like this. It looks just like that. It's all done with wire wrap. It's good. It's John says it's good for digital because in digital you're only usually trying to resolve the difference between 0 and 1 volt, or maybe 1 to 5 or something. You're not trying to resolve anything too small. Just on or off.
And especially when they were prototyping some of the early computers, like I would say the back stays on, maybe at post-fax. And a lot of it was wire wrap construction commercially.
Yeah.
Yeah.
VAX might have been, digital computers back in the days of that.
Yeah. So you'll see this, and there's an entire book called Soldering by Tracy Kidder that goes through the development of one of these computers, and they talk a lot about design your circuit. And then under here, there are copper traces. Maybe you barely see them, the contrast isn't great, but there are copper traces that connect the pads of different components to where they should go. And there are actually copper traces on the top and bottom of the board. So you have a way to get around routing things around each other. And these now are pretty cheap to have made. A 2-layer board, so copper on the top and bottom. You can now get 3 copies of it for about $5 a square inch, which is stunningly cheap. From the time you submit it to the time you have it on your desk, it's 10 to 15 days. Years ago, this would be done by somebody with tape. It was called taping the board. And they would tape out where all the connections would go. There's this long photo exposure process. It was very expensive to do. Now it's cheap. You can get boards that have multiple layers of copper. So a 4-layer board, for example, has copper on the top, on the bottom, and 2 internal copper layers that are insulated. So you can route signals inside the board. The downside of this is, if you mess up, it's pretty hard to change anything because all of those copper traces are hidden under this solder mask that goes on top to keep the solder from being where you don't want it to be. So it's a pretty permanent design decision. You can do sometimes with bodge wires where, okay, my maybe I meant for this to be connected up here, so I solder a wire there, and I solder a wire there, and run it across. It can get by. On 4-layer boards, it's pretty hard. You have internal conductors that you can't get to. The only thing I've ever been able to do, and I've messed up designs on those, is tape what's inside the board, print out of it on top, and try to use a very small drill bit and drill out that connection that I don't want. It's hit or miss if it works. But I'm going to send around a couple of examples. So this one has some parts on it. Some of the parts are through-hole, like what you're going to be using, that have leads that actually go all the way through the board. Others just mount to the surface. It's called SMT, or surface mount technology. So this is an amplifier that you can use for like a load cell. And this is actually a full processor board, analog to digital converter, all kinds of good stuff on it. This is a 4-layer board, so 4 layers of copper, they're believe it or not. $10 a square inch. This is a 2-layer for $5 a square inch. And the tools to design that are, there are some that cost you $10,000 a year, but those are designed with a free open source tool. No problem.
Is the 2 layers inside this board or just on the boundary of the board?
So there are 2, if you were to cut that board open, what you would actually see is there's a layer of copper and then fiberglass, and then a layer of copper, fiberglass, layer of copper, fiberglass, layer of copper, all inside that. It's 62 thousandths. Yeah, 1/62. So pretty amazing technology. When you're looking at your cell phone or your laptop, those are 10 to 12 layer boards. So they're much more complicated. Okay, so soldering. The one thing that all of these have in common is that we need to solder connections together to make anything that's semi-permanent. Soldering is a pretty basic technique, but it takes a long time to master if you're doing really small parts. If you're going to be soldering wires together like this, we can have everybody in here doing it in a few minutes. When those boards come around, you'll look, actually, I'll borrow that for just a second. So if you look, there's this one right here that's got a bunch of little tiny copper pads. This is, I think, a 44-pin device, and the pads are 1 millimeters apart or something. So soldering that by hand can be done, but you have to do it under a microscope and very carefully. So there's a bunch of different levels that you can go into. The most basic thing about a soldering iron, though, is one, it's very hot. You're dealing with something that is roughly 700 Fahrenheit. So it goes into your skin very quickly, and it's very painful. It will also, if it falls out of its holder onto the ground, it's a pretty good way to start a fire or burn holes in your carpet. But the most important thing is to get a temperature-controlled soldering iron. You'll see things like this that just plug into the wall. You can buy them for $9 at Home Depot. We call those fire starters, and there's a really good reason. You plug them in, and they have one temperature, which is excruciatingly hot. If you try to use something like that on one of those circuit boards with really small pads, you would actually melt the glue that holds the copper down, and the pad would come off, and the circuit board would be completely ruined. Or you can thermally damage components if So you don't want to use that. You want to get a station that has a temperature control. It can be a knob, it can be a screen that shows you what the temperature is. You can get a really good soldering iron, like that one on the left is $99. They're not bad. The one on the right, you can get on eBay, I think, for 30, 40 bucks. It's probably not going to be as good, but it could be just fine for what you want to do. But if you don't have something that's variable temperature, you will just get frustrated very, very quickly. Also handy to have, you see these have stands with a sponge. You use that sponge, make sure it's wet, you use it to clean the tip off. There will be black oxidation that builds up on the soldering iron tip. And then in here, you can actually put a piece of Brillo pad. When you have really stubborn oxidation, you can wiggle the tip around in there and get it cleaned off. There are a lot of different soldering iron tips, and there are bordering on holy wars of what the best one to use is. I will tell you my opinion that the narrow chisel tip is the only soldering iron tip you will ever need in your life for electronics work. These pointed conical tips, they go down to a really fine point, are borderline useless. I think everybody will agree on that you talk to, because they have such a small contact area on the joint that getting a good actual rate of heat transfer to your device is impossible. It will take you way longer to heat up a joint with that, and you may not ever even get it hot enough. There are specialty tips like this. It's actually called a hoof tip. It's got a little cup in there. You use this for very specialized small surface mount soldering, like what's on that board. You can fill that little cup with solder and drag it over all the small pins and solder them. But this little screwdriver looking here chisel tip is what you want for almost everything. Almost all of the parts on that board, the 4-layer, and everything on the 2-layer board can be done by hand with one of those chisel tips.
But all the soldering irons that you're gonna run into, those tips are simple to change. So you buy a bunch of tips and push it on, obviously not with your hand when it's hot, but it takes 2 seconds to change the tip.
Yeah, and they're cheap. They're $6 to $8 generally. There are companies that make professional soldering irons that you would pay $600 or $700 for the iron and probably 30 bucks for a tip. You probably never need one of those unless you're in a production environment. These do have copper cores, and occasionally you will find the need to make your own tip. I've done it for melting heat stakes, which are little plastic things that hold boards into a product. So you can chuck these up in a laser drill press and customize them because they're cheap enough. It's no problem. Solder is obviously one of the other things that you need. There are a lot of different kinds of solder out there. Never use plumbing solder, but you buy at Home Depot. That is containing acid inside and will quickly destroy everything that you're working on. You can buy from SparkFun, from DigiKey, from through wherever. These rolls of solder, it is expensive to get a good size roll, but a 1-pound roll will probably last you for 10 years, so it's not a problem. There's leaded and lead-free solder. It's a small percentage of lead that's in the leaded solder, and leaded solder is much easier to work with. It flows better, and the joints are actually stronger. Don't know if people remember, I think it was the 2011, one of the Mac products, one of their laptops had a big problem with, it would stop working after a while. It's because they use lead-free solder, which is more brittle, and the joints started breaking. So it does have some disadvantages, but if you're going to sell a product, especially, I think it's almost mandatory now in the US, it's definitely mandatory in the EU. It needs to be what's called RoHS compliant, it's RoHS, check mark above it. That means it needs to be lead-free, it needs to be recyclable. So if you're making something commercial, you need to use lead-free. Otherwise, especially when you're going to use software with lead in, or solder with lead in it, and make sure you wash your hands before you drink. Touch your eyes.
Just working with lead-based stuff is really nasty. And, Tom said, yeah, you're not gonna use the kind of solder that you could get in the plumbing section of Home Depot. And it doesn't look that different. It's always thicker, right? But picture it's for plumbing work where you're gonna be working what people call copper sweat, where you're gonna heat up a piece of copper pipe and solder it together. You're using a torch, not a soldering iron. And you're definitely not using lead-based solder because water that someone's gonna drink is gonna run through it. That's not an old problem, because but it's, 50 years ago, everyone's plumbing their house in the United States had that in it. Now, most people don't, and some people still do.
And this solder, I think the smaller the gauge solder you use, generally for electronics work, the better. You can always feed more solder in, but if you have this really big, thick soldering wire, it's hard to get a small amount on. This solder is 31 thousandths of an inch in diameter, so about 0.8 millimeters, and I would consider that large for electronics work. I try to use something that's in the mid to low 20s, thousandths of an inch diameter. What's incredible is that there is flux in here, which flux is a compound that cleans the joint when you heat it to make sure that you've got a nice clean surface to work on. And it's most of the solders like that, even in that 20-something to 30-something thousandths, they have 6 separate cores of flux inside. So a lot of really fine structure in there. It's a metallurgy problem. There are volumes on different kinds of solder. So here's some examples of flux. If you're making a new connection, say you twisted some wires together, you put a part through a board, and making the first connection, you generally don't need to apply flux unless things are really gross. The flux in the solder is going to be enough. But if you're reworking a connection, so now you want to remelt the solder, add something else to it, take the part out, whatever, you need to add flux to make sure that everything gets cleaned again so you get a good joint. Flux can come in these little syringes that you can just put a tip on and squeeze out. There are little guns that you can put that in. There are air-driven things. The easiest way to do it, though, I think, is to grab one of these flux pens. They're called, which have a felt tip. They're filled with flux. They're about $5. You dab it onto the board where you're going to work, and when it runs out, you throw it away. Grab it back in your toolbox. That is a very thin water-like compound. It does flow around quite a bit. If you need some help sticking your components down to a board, they're really small, they're really light, they're moving. These fluxes that are in the syringes are a lot thicker. They're kind of like jelly paste. Once again, everybody has an opinion on what the best flux to use is. You have to buy about a dozen to just figure out what. Desoldering, or taking the parts off the boards or undoing connections, can unfortunately be a pain a lot of the time. There are a few tools to help you do it. This is called desoldering braid. It's very fine copper strands that are braided out with air into this flat material. And you put that on top of the soldering joint, put your soldering iron on top of it, and it heats, melts the solder, and just by capillary action, the solder gets sucked up into that braid. And when it cool, you cut the piece off that's filled with solder, chuck it in the trash, and go on. That's pretty cheap, and it's worth, I think, so this is 1.5 meters in this little roll. You can get a lot bigger rolls, and I recommend doing that. Another tool on the right is solder vacuum. This little plunger, when you press down, it locks. You melt the solder joint. You stick this tip up there by it, press the button. The plunger retracts, and it just vacuums the solder off the joint. They work sometimes. What's tricky is if you have a part that has, say, an integrated circuit that has 16 pins sticking through a circuit board. Neither of these techniques is going to remove all of the solder. So you have to have everything removed to pull the part out. So you could play games with moving the soldering iron around, trying to make sure everything's hot. You could just cut the leads and remove the pins one at a time if you didn't care about taking it apart. Or there are special soldering irons that have a hollow tip that goes over the pin. You melt it, you squeeze the trigger, and a very strong vacuum sucks all the solder out.
But you can't read this slide with the bland description you've given so far. Because you never use this stuff unless there's been essentially a major fuck up. Okay? Because you've reached the point where you realize you made the wrong connections and you don't have another one of these. You can't just cut it and throw everything away that you're working with. You've got to save it. Or you've made a board that doesn't work and you're not sure why. So I mean, I feel like you never use this stuff without already being kind of pissed off.
It's true.
That you're at that stage and you're having to carefully
Yeah. Well, and
take it apart.
there's also a product called Chip Quick that you can buy. It's a much lower solder that you glob on top of all of these joints, and it stays molten for a longer time. It makes an alloy with the solder that's there. So you can have all of those pins melted at the same time and pull your part out real quick. The other technique for surface mount parts, like some of those that you saw on those boards, is by using a hot air wand, which is basically a hot air gun, and you melt all the solder connections in one area of the board at once, and then you just take tweezers and pull the parts off. I have done that even though there hasn't been a major problem, just because some parts are really expensive, not generally, but yeah, I dealt with integrated circuits that are the size of that little one on there that cost $50 per unit, so I didn't want to buy a lot of them. But yeah, generally something's gone pretty wrong with this kind of stuff. So to do soldering, first thing is to prepare your work area. Make sure there's nothing like a bottle of acetone sitting nearby. Get a virus. People will happen. Make sure you got your circuit board secured in some kind of device, or clamp, 13, whatever you want to use. You got your soldering iron, your stand, and then some flush cutters to cut off extra bits of lead that are sticking through. You turn your soldering iron on, you get it all heated up. I think that everything we have in the lab right now, I think I've set to Celsius. I think those 345 Celsius is a good round number for solder, which is what we have. I can put a little bit of solder on the tip of the soldering iron and wipe it on the sponge, so there's this real thin coating there. It's called tinning, the tip of the soldering iron. And clean your board. Here they're showing using a paper towel, which you can do. You can really little fibrils everywhere. It's hard to get off. There are these things called clean room wipes that you can buy from your MasterCard, $15 a half that don't shed. But you'll take a little bit of isopropyl alcohol, put it on something, wipe the board down to make sure everything's good and clean. The most important part, and if you look, there's a page, I think it's linked on the website, if it's not, I will link it, that is the NASA standard for how to do soldering. You can imagine it's pretty insane. But you need to make a secure mechanical connection. Solder is generally not considered a structural component. If you're using it as a structural component, maybe otherwise. So this could be just sticking the part through the board and bending the leads way out so that it's not falling. If it's two wires, you want to do a really good twist connection of them together. Then you take the tip of the soldering iron. Here is where the chisel tip comes in handy. You see that little contact area they have with this conical tip. With the chisel tip, you get a lot of energy transfer. And you make sure that the entire joint is hot. So you're touching your pad or the other thing that you're going to solder and lead. You'll hold that for a couple of seconds, let things get good and hot. And then you feed the solder wire into the joint. You don't have to touch the soldering wire to the tip of the soldering iron if everything is hot enough. If the joint should be able to melt, the entire joint should be hot enough. And let it cool. You sometimes see people that solder something and immediately start blowing on it, and that creates what's called a cold solder joint. It's a very brittle configuration of solder. It will look glazed over and not nice and shiny like these do. If it doesn't look like a shiny miniature volcano, it's not right. You need to put some flux on it and try again. Then you'll take these flush cutters in here and flip off any excess wire that's sticking through. This, I'm not going to go through, but it's in the slides that are going to be on the website later this afternoon. It's just a handy thing that shows you kind of steps in case you forget, and shows you some common problems that people have and solutions. How to fix those. And yes, it's a bad connection. And also a thing. So it's a pretty fun guide. There are other ways to do soldering. So this is it's actually a mediation camera. But it's when you buy commercial products, a lot of them are what's called reflow solder, where you use solder paste that you squirt out of a syringe. It's got little balls of solder suspended in just some kind of it's probably flux coming out. And you would squirt that onto everywhere that there's going to be a connection, and you set all the parts on those connections. So you have parts sitting on solder base, sitting on pads, and then you put it in an oven. Commercially, these are half the length of this room, and a board goes through it. There's various temperature stages, and they cost about $10,000 a month in electricity. We obviously don't need that because these boards are very small, and we're not going to be making production quantities of things. So you can take a toaster oven, not the same one that you use for food, obviously, because there's lead in it most likely. board passes over it, and because it has that solder resist layer on it, we don't want connections to be made. The solder sticks to the connections, doesn't stick everywhere else. It's a really quick way. If you take something apart and you see an arrow, sometimes on boards over an arrow, it says dip. That is the direction that it's supposed to go through. The soldering process. Okay, so it is 10 to 1. And we've got an activity to do, and then folks that haven't done threading that want to get started on it, and we can go to the lab here in just a couple minutes after a few houses, and you can get started on that. Basically, what you're going to build is what's on this breadboard. It's a slight variation. You have to do a little bit of programming. You have to modify the Linky program that we did last week. And you're going to put 2 LEDs on your external breadboard, and not horribly exciting, but it's going to show you how to use the breadboard and get you a little bit more comfortable with writing some code to the Arduino. This is going to lead up to an activity that's coming next week where you're going to build a stoplight. Actually, that's just react to like a car and these kind of situations. The other thing is this, showing people in their meetings that there are things called power switches, where you can plug it into the wall, plug some device into it, say a lamp, and it connects right to your Arduino. And as simple as turning this LED on or off, you can switch on or off lamps, refrigerators, whatever you want to do. So it's actually a pretty useful activity. But I tried to stress this in the instructions. I want to go over it really quick. You're going to be using LEDs, and LEDs are polarized components. It means they're the right way or wrong way to put them. So they're diodes. LED stands for light emitting diode. So we know we haven't gone over the function of diode yet. This is a diode, whole schematic. How do you draw it? This is an LED. It's the diode symbol with light coming off of it. You'll see that when you take out an LED out of your kit, that there's a shorter leg and a longer leg. The shorter leg also has a flat side on the LED. That marks the cathode. And the longer leg, or the leg that does not have a flat side on the LED, is the anode. Current flows from the anode to the cathode. And it's what's called conventional current flow. It's not linear. Current cannot flow the other way. So if you put your LED in your circuit and it's not doing anything, it's very possible that it's in balance. Has everybody seen on the LED the leg difference in the flat spot? Did you find that? Okay. The other thing that you'll see is you have to have a resistor in the circuit. So it's just a battery and a resistor and LED. And it's called a current limiting resistor. If you just hook an LED up to an ideal power supply that could provide however much current it wanted, it would very quickly let out this little pop and puff of smoke and then feed into that LED. Because we try to push too much current through it, and it actually destroys the silicon die that's inside. So this resistor limits how much current can flow through the circuit. And there's a web page that tells you how to calculate it, but for today you're going to use the 330 ohm resistor that's in your kit. And that will keep everything nice and safe for all of your LEDs. Alright, assignment for those of you that have already had your meeting, like we'll have it tomorrow, this is going to be very important. Next Thursday, you should turn in your project proposal, which is a one-page document. I'm going to add a little bit of more specific instructions to the page later today, but a one-page or less document that's a couple paragraphs about what you're going to build exactly, so what problem it solves and how you're going to solve it. And a parts list, so something that can justify to yourself and to us that you're not going to propose something that costs $1,000. Kind of shooting for $60. The summary of everything that's going on, make sure everybody's on the same page. The threading activities that many of you have already done, and I've got a box of things that people turned in over here. You need to have this physical object in our hands by Tuesday. The tools will be available to do that in the lab.
too on the website.
Yes, if you go to the lab exercises and Blinky 2.0, there's an instruction set on how to do it, just very similar.
Right, and if you haven't looked there, that's also a place to look for the threading activity, right? All the details of the threading activity are on the course website. If you want to just bring it up,
Yeah.
they're on the course website, they're simply listed there as an activity.
Alright, so if you go to lab exercises and there it is. Lab exercises, here's Blinky 2.0. There's a nice scripting diagram here that shows you what the layout on the breadboard is better.
And remember now, when you look at your board, your breadboard thing, if you look carefully at it, you'll see a whole bunch of numbers going from top to bottom, and 1 to 30. And each one of those is a little bus. So anywhere you plug in row 1 connects to A, B, C, D, or E. Okay? So each one of these is a little bit of a little bus that's going to allow you to simply connect. You know, if you take your resistor and go from plus into row 10J, then you can plug the next thing into row 10 anywhere else, and you'll be connected to it. So, I mean, maybe it's obvious, maybe not, but the whole thing that's cool about this is that it's got all this row and column bus structure to you to give you what you need, without being complicated.
Right, and for the resistors, okay. If you look at your resistors, so they're in a marked package right now. That may not stay that way for long, especially when you've got a bunch of them. See, there's different colored bands on them, and those colored bands